Good afternoon, everybody. So this is our 416 development and growth. And today we're going to finalize our discussion of endogenous technology and productivity and so on and so forth. So let me share my screen. Today, I have three issues to cover. One is the technology adoption model. Okay. One is technology adoption model. The second is risk and uncertainty in innovation. Okay. And the third is that evolutionary foundations. So for this, I'm basically using a particular approach that is developed by Joel Moyker in his 2002 book, Gifts of Athena. This is a very nice book. I would strongly recommend for you to check if you are interested in the history of knowledge and technology. So it is basically an economic history book, but it covers, in the first chapter actually, it covers a nice informal theory of knowledge and technology. Okay, so I will discuss that briefly for you to gain some further understanding of innovation and technology adoption. Okay, so let me first start with the risk and uncertainty part, because this is, so remember, we are interested in three sources of productivity growth, right? Three sources of productivity growth. The first source was sectoral reallocation of resources. The second one was innovation. And the third one is technology adoption, right? So if you imagine the production possibilities of a country, you can put many stuff here, including labor, and then you have that productivity term. And we are interested in understanding how that productivity change actually occurs in an economy. All right, so let me first start today with risk and uncertainty, then we're going to cover technology adoption, and finally, again, we're going to discuss some of the evolution foundations. Now, the problem with innovation is this. Usually there is a sunk cost, okay? So imagine this as the initial spending on machinery, equipment, and skilled labor. Okay, there could be other stuff that you can imagine, but typically for innovation, even before you start the research and development work, okay, even before R&D actually starts, you have to establish your research firm, okay? You have to spend some money on machinery, equipment, laboratory, and you have to find the skilled labor. Sometimes, since it is highly specific type of knowledge, you have to actually train these people, okay, for innovation. Now, obviously, in a modern capitalist economy with a well-functioning scientific system or science and technology base, you will find skilled labor somewhere in the society. So they're going to be graduates of certain universities and certain programs, but you still do not know whether these sunk costs will pay off, right? So you face the uncertainty, and typically what we imagine is this. Suppose that RT or R is total research spending. This may include the sunk costs, okay? Now, typically, we are interested in this probability. Probability of successful innovation conditional on the money you spent and other stuff, right? That other stuff could be the technology of production, right? I mean, here we are talking about knowledge production. Now, let's denote this probability with P, okay? Now, what you are interested in, of course, is to write your expected payoff or expected profit, right? So as a prospective entrepreneur or a firm, you are interested in expected payoff or profit from innovative activity. Okay. Now, there will be, of course, two cases, right? Suppose that X denotes a particular innovator's success or failure, right? So it will be equal to success with probability P, right? And it will be equal to failure with probability 1 minus P. So it is like a Bernoulli event. Okay. Now, this is not the only way that we can model uncertainty in innovation. Okay, there could be other ways, there could be other functions, other models of such, there could be other type of probabilistic events for technology or successful innovation. But in the simplest possible case, we're going to spend some money, and then at the end of it, we're going to either be successful or not successful. Okay? So you have then something like this. The expected payoff, let me denote it by this. Okay? It will be simply a weighted average of probability of success, right, minus your spending plus 1 minus P times profit of failure minus R. Now, obviously, since P is a probability, it is typically between 0 and 1, and more specifically, we may assume that it is interior, right? So it cannot be 0, it cannot be 1, but it is a positive number that lies strictly between 0 and 1. Okay? Now, what about the success profit? Now, of course, it is meaningful to assume that success profit will be positive. Okay? Now, failure profit could be 0 or maybe positive as well, but in general, we're gonna assume that P success is greater than, so pi success is greater than pi failure, right? So that's the meaningful assumption. Now realize that you make the research spending in any case. Okay, that's the foundation of this particular approach, right? So you have to make that spending. Then your scientists and engineers work on this particular problem or machine or innovation or process or product, and eventually either they become successful with probability P, or they become unsuccessful, the project fails, and that's the probability. So that happens with probability 1 minus P. Okay, so before spending R, okay, before spending R, you want to think about the expected profit or expected payoff. Okay, now what I said earlier could be written more specifically in this way. Suppose that probability depends positively on the research spending. Okay, so if you spend a lot of money, okay, if you spend a lot of money, you increase the probability, but perhaps if you increase it too much, there is decreasing returns to scale. Okay, now if you consider all these together, how can you write the expected profit? Well, you will have PR times pi success minus pi failure. I'm just doing the math here. Okay, then what do I have? Minus R, right? So I basically replace this with PR and I open it. It is certain that I am making that spending, right? And with some probability that depends on my spending, I'm going to be successful. The difference between success probability, success profit and failure profit gives me the profit margin. Okay. And here I am assuming that this is a timeless problem, right? So there is no time involved. When there's time involved, the problem is slightly more complex. Okay, but for understanding the simple mechanics, we can look at this version. Now, of course, you may want to maximize this expected profit by choosing R, okay? But you have to be careful with the non-negativity constraint here, right? Because maybe R equals 0 is optimal, maybe R equal positive is optimal. Okay. So this is the mathematical version of the problem, right? And here we assume that, what do we assume? So let me write the problem once again in a clear page. So the problem seems to be to maximize this expected profit, and expected profit is written in this way. So there is a probability of success, and that success probability depends on research spending. Then there is this profit margin, the difference between success profit and failure profit. And then there is the research spending only as a cost. Okay, and you want to maximize this by choosing some level of research spending. Okay, what do we assume here? We assume that the entrepreneur knows PR, right? We also assume that he or she knows pi s, he or she knows pi f. we also assume that he knows optimization, he or she knows optimization theory. Okay, so there are a lot of foundational assumptions here. Some of them are not really true, but that would be the idealistic case if really a rational entrepreneur, okay, or fully rational entrepreneur tries to find an optimal result. Now you can surely write this model. You can further specify PR. Okay, for instance, you can tell me that this probability can be written in this way. Okay, so here alpha is positive and beta is between 0 and 1, for instance. Okay. Now what happens? Well, this tells you that, first of all, P0 is positive, right? Because P0 is equal to alpha to the beta, and it's a positive number. Okay. So this means that even if in that particular version, so maybe I can generalize it by saying this. So if alpha is positive, if it is strictly positive, then this means even if this firm spends no spending, if this firm or entrepreneur makes no spending at all on R&D, there is still some small probability of success. Okay, possibly some of the workers or some of the engineers or the entrepreneur himself or herself, they're gonna come up with the bright idea, and that idea will require no spending. That could be the case. Or alpha is 0. Okay, so this is true if alpha is positive. If alpha is 0, this is of course 0. Okay, but if you know what PR is, you can solve this problem, of course, if there is a solution, right? Because you maximize this. This is just now a mathematical problem. Beta times this difference, which is exogenous for now, minus R. Okay, so you choose R. Now I'm gonna give that to you as an exercise. Okay, try to solve this problem in two cases: alpha equals 0, alpha greater than 0. Okay, and maybe we can discuss later on your solutions. Okay. So this is that. So of course you can write more detailed stories about these profit levels. Okay, so you can start with the production function first. So this firm, let's say, will produce some output using capital and labor. So the profit, let's say, and suppose that there is also productivity, of course. Okay, so the profit will generally depend on, will generally could be written in this way, right? This is what you know from your micro studies. I am normalizing price to 1. So price is here, but you can normalize it to 1. If there is success, okay, if there is success, you work with a more productive technology. If there's failure, you work with a fixed productivity. Okay. So the difference will be generated by the research sector, of course. So here, typically, this must be the case. Otherwise, there is no point in spending research, right? So pi s will be greater than pi f. And then you can, again, if you solve these problems first, then what the solution is going to look like? Well, the solution is going to look like each profit level will be a function of prices, right? So it will be a function of prices, and it will be a function of productivity level and some other stuff if necessary. And so parameters are going to be there. And then you can also write general equilibrium versions of this, blah, 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 blah. So I'm not going into that detail. So a detailed model, of course, could be established. So do you have any questions about all this? The main idea here is that most of the time in innovative activity, risk and uncertainty plays a huge role, okay? And this is the simplest type of understanding, simplest type of model where you see that there's a profit margin and there's a success probability. Typically, success probability is positively changing with how much I spend, because if I spend a lot, I can find the best engineers, I can find the best equipment, I can find the best computers, and so on and so forth. So there are trade-offs, right? So I'm spending money today for the expectation of finding a successful innovation, and that successful innovation, as you see here, is going to increase my productivity, okay? Kind of. Or there will be a new product innovation, so you open a new market and you start selling a new product. So in any case, there will be a profit margin that would incentivize innovative activity, okay? Now the problem can be also approached in a policy perspective, okay? Now suppose that there is, so the process, suppose that the R&D process has multiple stages, okay? So stage 1, stage 2, stage 3, that goes on until, let's say, state K. Okay, so these are, maybe I can have a better, so these are stages 1, 2, 3, 4, that goes on, some generic state S, and finally there is the final stage, okay? Let's note it by F, the final stage. Now, the idea is that for each stage, there is a success probability, okay? So this is like what? This is like the Cramer's model, right? O-ring model. So there are various stages, and each stage has a particular probability of success. Okay. Now, imagine this. In the earlier stages, it is basic research, right? And in the later stages, it is applied research. So this is more like science. This is more like technology. And why does that matter? Can you explain why? Can somebody explain why that difference is important?
Because there is a two-way relationship in here. If there is no science, we cannot make make technology. Maybe this is the reason.
Okay, so this is okay. This is correct. So obviously, in this particular understanding, basic research supports applied research in a linear manner. So first, we understand the scientific aspects of this particular product or process, and then after certain number of stages, we apply this science to the realm of technology, and in the technological realm, we try to develop this product or process. Okay, that's fine, but there's more to it. Think about the policy, think about the role of the state, think about the role of universities, for instance, or the concept of entrepreneurial state. You know that many of the technologies that we use today were actually developed initially by huge investments by the governments, right? Why is that? The reason is, again, about the uncertainty, right? Now, from the private sector's perspective, the earliest stages are truly uncertain, right? Because firm is interested in this profit, right? So now the overall success probability is the multiplication of all of this, right? P1, P2, dot, 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 PF. So each stage is important. And if I am the firm that will make the spending R, and if there are too many stages, and if I cannot really predict the success of the project when it is at the basic research level, then I cannot really find this type of investment. I may not really find this type of investment optimal as the private sector firm. So from the optimality point of view, from the public policy point of view, for many projects, there is a particular stage, such as S star, right here, for instance, okay? It tells us that optimally, the government should support basic research until the success probability at this stage is large enough for private firms to enter the market, or for government to stop subsidizing research, because applied research part will be already profitable for the firm. Okay, so that's important. And this doesn't necessarily imply the optimal stage will be exactly right here. Maybe optimal stage can be here. Okay, so some of the basic research will be done by the firms, or it may be here, where some of the applied research is made by the government. Okay, so there's no easy way to measure all of this, but let's find the technologies that initially supported by the government. The most obvious example, of course, right now is the internet, but GPS and smartphones are also supported and initially designed kind of by the government. Okay, there are others. If you look at military technologies or technologies that find their initial success in military area, those of course are government supported or government initiated technologies. GPS is one of them, actually. So there is that side of it. All right. So when we say that private sector or markets are always good for innovation, we still need to think about how to optimally design research policies. Okay, and optimal research policies is, of course, hard to define, hard to measure, but this is, I mean, what I'm showing you right now is a particular model where it is shown that such an S star will be Pareto optimal for the society to generate the highest level of welfare in that particular sense. Okay, and it would be an interesting case study. So, for instance, if you look at different industries and different types of innovations, and try to understand how much of the or how many stages of the research and development process of that particular innovation actually was supported by the government, or how much of it was actually the pure pure work of the private sector. For the biggest technologies, you may find only little business involvement. So in the early stages, there is huge investment by government and other public institutions. Not just, I mean, it doesn't have to be government. It could be universities. It could be other, institutes and all other things that use basically public funds for certain purposes. Okay, so that was the other thing that I wanted to share about risk and uncertainty. And there are many others. If you look at the textbooks, I recommend especially Weil's text. So you will find even further discussion about such aspects of innovation. There are other aspects such as increasing returns and decreasing average cost in the long run. There is something called weightless economy. For instance, you can check Danny Quast's earlier work on weightless economies. Okay, the idea is that in the knowledge sector, there is no physical mass, right? So imagine YouTube videos. You create YouTube videos, but there is no physical mass of these products, right? So production is totally different for certain technologies, and that cannot be easily captured by standard Codd-Douglas production functions that we always use. Okay, so there are many other side issues that you can actually study. So let me stop sharing and pause here for a moment. So if you have now questions and comments, you can share it. Otherwise, we're going to take a break and continue later on.
Hocam merhaba. Ben dersin başını kaçırdım da biraz. Cevap verdiyseniz bilmiyorum. Ödev yükleyeceğim demiştiniz. Bu hafta mı yükleyeceksiniz?
Evet yükleyeceğim bu hafta. Bir aksilik
Tamam hocam.
çıkmazsa yüklerim birkaç güne. Bir iki güne yüklerim.
Teşekkür ederim hocam.
Rica ederim. Okay then, so let's meet at 2:55, okay? Because I need that time for video conversion. Then we're going to continue with technology adoption, okay?
Tamam hocam.
Let's meet at 1:55. Bye-bye.
Tamam hocam, görüşürüz.